The morning sun glinted off calm waters east of Saipan as Lieutenant J.G. Alex Vraciu rolled his F6F Hellcat into position, his wingman tucked in tight beside him. June 19th, 1944. The date meant nothing yet, but by day's end it would be written in blood and fire across the Philippine Sea. Vraciu scanned his instrument panel, then looked out at his aircraft's broad wings, each folded at an angle during pre-flight checks by deck crews, using Grumman's patented mechanism. Those wings, with their distinctive diagonal fold lines running from the fuselage outward and aft, were about to be tested in ways their designers never anticipated. Within hours, Japanese pilots would discover that the very feature designed to save space on crowded carrier decks had accidentally created one of the most structurally resilient fighters ever built. The Sto-Wing wasn't designed to stop cannon shells. It was designed to fold. But in the brutal mathematics of aerial combat, those heavy-duty hinges, reinforced spars, and redundant structural members would prove nearly as important as armor plate. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Grumman F6F Hellcat that Vraciu flew that morning represented the culmination of American naval aviation's rapid evolution. Designed in early 1942 and rushed into production by that summer, the Hellcat had been built specifically to counter one aircraft, the Mitsubishi A6M0. By mid-1944, it had become the dominant carrier fighter in the Pacific, accounting for 75% of all U.S. Navy aerial victories. But the Hellcat's success wasn't purely about performance. It was about a design philosophy that prioritized pilot survival and structural integrity above elegant simplicity. While Japanese fighters pursued grace through weight reduction, Grumman built what pilots affectionately called the Iron Works. Every component was overbuilt, every system had redundancy. And one of the most over-engineered features on the entire aircraft was something most people never thought twice about: the wing folding mechanism. The Sto-Wing, as Grumman called it, had been invented by company founder Leroy Grumman himself, using nothing more than a drafting eraser and 2 paperclips. The legend goes that Grumman, frustrated by months of failed attempts to create a practical folding wing, sat at his desk one evening in 1941 and began playing with office supplies. He stuck 2 paperclips into an eraser to represent wings, then bent the short ends perpendicular to the long clips. When he folded them back, they moved on a skewed axis, rotating diagonally upward and aft simultaneously. The angle was specific: 63 degrees and 40 minutes from horizontal, 28 degrees and 30 minutes from vertical. This diagonal pivot solved multiple problems at once. Unlike straight-back folds, it didn't increase the aircraft's height significantly. Unlike vertical folds, it didn't require impossibly strong hinges to support the wing's weight when extended. The skewed axis distributed stress across multiple planes, making the mechanism inherently stable. But here's what Grumman's engineers discovered during development. Making the Sto-Wing safe enough for carrier operations required extraordinary structural strength. The hinges had to withstand the violent shock of carrier landings, where an F6F hit the deck at 14 feet per second with all 12,000 pounds slamming onto gear that was mounted inside those folding wing sections. The pivot points had to handle not just the static weight of the folded wing, but the dynamic loads of catapult launches and arrested landings. The locking mechanisms had to be absolutely fail-safe, because a wing that unlocked in flight meant instant death. So Grumman built the Sto-Wing mechanism like a bridge. The pivot axis wasn't a simple pin joint. It was a complex assembly of forged steel components, heavy-duty bearings, and massive structural members that tied directly into the main wing spar. The wing spar itself on the F6F was a single forged aluminum beam, 4 inches thick at its center where it passed through the fuselage, tapering to 2 inches at the fold point, then continuing into the outer wing panel as a lighter but still substantial structure. At the fold line, where the fixed inner wing section met the folding outer panel, engineers created what amounted to a structural fortress. Multiple attachment points distributed loads. The hinge assembly was massive, far heavier than a simple folding mechanism needed to be. Hydraulic actuators could fold the wings in seconds, but even when operated manually by deck crews, the system was over-designed to handle forces far exceeding normal operation. This wasn't intentional armor. This was simply Grumman's obsessive commitment to making aircraft that could survive carrier operations, which were inherently violent even without combat damage. But the unintended consequence was that the wingfold area on every Hellcat became one of the strongest sections of the entire airframe. Stronger than the wing root where it joined the fuselage. Stronger than the wing tips. Stronger, in some ways, than the fuselage itself. Japanese pilots in early 1944 had no idea about any of this. What they knew was that American fighters kept getting tougher. The F4F Wildcat had been difficult to kill, requiring multiple hits to bring down. The new F6F seemed nearly invulnerable. Pilots would report hitting Hellcats repeatedly with 20mm cannon fire, seeing their rounds strike home, watching pieces fly off the American fighter, and then watching in frustration as the Hellcat simply kept flying. By June of 1944, Japanese naval aviation was dying. The elite pilots who had dominated early war combat were mostly dead, killed in the grinding attrition over the Solomons, New Guinea, and the Central Pacific. Their replacements had minimal training, sometimes less than 300 hours, compared to the 1,000+ hours American pilots received. They flew aircraft that were increasingly obsolete, with no armor protection and minimal structural reinforcement, and they faced American pilots flying Hellcats in numbers that seemed endless. The Vraciu told the story. In November 1943, at Tarawa, Hellcats had shot down 30 Zeros for the loss of one F6F. At Rabaul, the ratio was nearly 50-1. By early 1944, Japanese pilots survived an average of just a handful of missions before being shot down. The mathematics of attrition were brutal and unsustainable. But numbers alone don't explain why Japanese pilots found the Hellcat so frustrating to fight. The Zero could still outturn the Hellcat at low speeds. Japanese pilots with experience could still maneuver into firing position. They could still hit the American fighters, but those hits increasingly meant nothing. Hellcat after Hellcat absorbed damage that would have destroyed any Japanese aircraft and simply kept fighting. Some of that was armor. The Hellcat had 212 pounds of cockpit armor, plus armor protecting the oil tank and cooler. Armor could stop rifle-caliber rounds, even some cannon fragments. But experienced Japanese pilots knew where to aim. They targeted the wings, where fuel tanks lived. They targeted the engine, aiming for the cowling or the massive Pratt & Whitney radial itself. They targeted control surfaces, trying to damage ailerons or elevators, and they kept failing to achieve kills. The Great Marianas Turkey Shoot began on the morning of June 19th, 1944. Admiral Mark Mitcher's Task Force 58, built around 15 fleet carriers, had positioned itself to support the invasion of Saipan. The Japanese mobile fleet, under Admiral Jisaburo Ozawa, was approaching from the west with 9 carriers carrying approximately 470 aircraft. The Americans knew they were coming. Radar had spotted the incoming strike waves while they were still miles away. Hellcats from 7 carriers scrambled to intercept, forming a defensive barrier between the Japanese attackers and the American fleet. By 9:30 that morning, over 200 F6Fs were airborne at various altitudes, with more launching continuously as deck crews worked with practiced efficiency. The first wave of Japanese aircraft, 69 total, including fighters and bombers, hit the American defensive line around 10 o'clock. They ran straight into the Hellcat barrier and were slaughtered. Of 69 aircraft in that first wave, 42 were shot down. The second wave, 128 aircraft, launched shortly after. Over 100 were destroyed. Wave after wave of Japanese aircraft came on throughout the day, and wave after wave was cut to pieces by the waiting Hellcats. Lieutenant Alexander Vraciu, flying from USS Lexington, shot down 6 Japanese aircraft in 8 minutes during one engagement. His squadron mates claimed similarly extraordinary numbers. The chaos of air combat over the Philippine Sea that day became the stuff of legend. But amid the one-sided slaughter, something was happening that Japanese pilots couldn't explain. They were hitting American fighters. They were landing shots. But the Hellcats wouldn't go down. One Japanese pilot, in a combat report recovered after the war, described firing an extended burst of 20mm cannon into a Hellcat's wing, seeing the impacts walk across the wing surface, watching pieces fly off, and then watching in disbelief as the American fighter simply rolled away and escaped. Another report described multiple Zeros ganging up on a single Hellcat, all firing simultaneously, hitting the aircraft, repeatedly, yet failing to bring it down before running out of ammunition and having to break off. Combat reports from American pilots told the complementary story. Hellcats returned to their carriers with damage that would have been fatal to any other fighter. One F6F landed on USS Enterprise with over 200 bullet and shell holes. Another returned with an entire section of wing fabric shredded away, metal ribs exposed, yet the wing structure remained sound. A third landed with both wings punctured by cannon shells, fuel leaking from multiple holes in self-sealing tanks, hydraulic fluid spraying from severed lines, yet the pilot walked away uninjured. What Japanese pilots couldn't understand without examining a Hellcat closely, was where all that structural strength came from. The armor protected the pilot. The self-sealing tanks prevented fires. But the reason Hellcats kept flying after taking wing damage that should have been catastrophic, that came from structural redundancy that Grumman had built into every section of the airframe, and particularly into the area around the wing fold. When a 20mm shell hit a Hellcat's outer wing panel, it encountered a structure that was overbuilt compared to equivalent Japanese aircraft. The wing spar was thicker, the ribs were heavier, the skin was reinforced, but if that shell hit near the fold line, it encountered something even tougher. The fold mechanism required such massive structural members that the entire area was essentially a box of forged aluminum and steel components. A shell could penetrate the wing skin, could damage internal structures, could even sever control cables, but it couldn't easily break through the fold mechanism itself. The engineering reports Grumman had produced during the Hellcat's development never mentioned combat survivability as a benefit of the Sto-Wing design. The mechanism existed purely to save space on carriers. The original specification called for reducing the Hellcat's 42-foot 10-inch wingspan down to something manageable when the wings were folded back alongside the fuselage. The engineers calculated stresses based on normal carrier operations. They tested the mechanism for fatigue life, assuming thousands of fold and unfold cycles. They verified the locking mechanisms would hold under the violent deceleration of arrested landings. But nobody thought to test whether those heavy structural members would stop cannon shells. Yet that's exactly what was happening over the Philippine Sea. Japanese pilots targeting Hellcat wings were discovering that some areas seemed nearly impervious to damage. Hit a Hellcat's outer wing panel, and you might damage control surfaces or punch holes in fuel tanks, but hit near that diagonal line where the wing folded, and your shells often accomplished nothing beyond cosmetic damage. The structural density in that area was simply too great. One particular engagement on June 19th illustrated the phenomenon perfectly. A Japanese bomber formation approached the American fleet at 14,000 feet, escorted by Zero fighters. A division of 4 Hellcats from VF-16 intercepted them. The Zeros immediately engaged, trying to draw the Hellcats into a turning fight. The American pilots refused the bait, maintaining speed and altitude advantage. One Zero pilot, more experienced than most in the rapidly depleting Japanese Naval Air Force, managed to get behind a Hellcat during a complex multi-aircraft engagement. He was perhaps 500 feet back when he opened fire with both 20mm cannon and his 2 7.7mm machine guns. The burst was well aimed, walking across the Hellcat's right wing from the fuselage outward. The American pilot, Ensign Richard Stambuk, felt the impacts and saw pieces flying off his wing, damage lights on his panel illuminated. Fuel pressure dropped slightly as one of the self-sealing tanks took hits, but the aircraft kept flying normally. The Zero pilot fired again, another long burst, emptying his cannon ammunition. more hits registered along the wing, more pieces flew off. The Hellcat's wing was visibly damaged now, holes punched through the aluminum skin, internal structures visible. But it wasn't folding. It wasn't breaking. The wing spar held. The fold mechanism absorbed impacts that would have shattered a more lightly built structure. Stambuk rolled right, dove away, and used the Hellcat's superior speed to escape. He made it back to USS Lexington, landed safely, and walked away, while maintenance crews examined his aircraft with professional interest. The damage assessment told an interesting story. The Zero's cannon shells had penetrated the outer wing panel in multiple places. They'd damaged 2 ribs. They'd punctured the fuel tank, though the self-sealing feature had worked as designed. They'd severed 1 control cable, though redundant cables maintained aileron function. But 4 shells had struck within inches of the wing fold mechanism, and those shells had accomplished almost nothing. 1 had glanced off a heavy structural member. Another had penetrated the wing skin but stopped when it hit the fold actuator housing. 2 more had struck near the hinge assembly and been deflected by the thick metal components there. The maintenance report concluded that the aircraft would require approximately 20 hours of work to return to service. The wing structure itself needed no significant repair. The fold mechanism was undamaged. Fuel tanks would be patched. Control cables would be replaced. Skin panels would be riveted over the holes. That was all. By the end of June 19th, the battle that American pilots would forever call the Great Marianas Turkey Shoot had cost Japan catastrophic losses. Of approximately 370 Japanese aircraft that participated in the day's strikes, 240 were shot down. Another 30 suffered damage severe enough to prevent recovery, crashing in the ocean or being destroyed in emergency landings. Japan's naval aviation had been effectively destroyed in a single day. The kill ratio told a brutal story. American forces claimed over 350 kills against only 23 losses to enemy action. Even accounting for the inevitable overclaiming that occurred in the chaos of air combat, the exchange rate was devastating, and most of those losses were to anti-aircraft fire, not enemy fighters. Of the hundreds of Hellcats that flew that day, only a handful were shot down in air-to-air combat. Japanese pilots who survived June 19th and the subsequent months of combat began reporting back to their intelligence officers with increasingly detailed observations about American fighters. The reports, when examined together, showed a pattern of growing frustration and confusion. Pilots described hitting F6Fs repeatedly with cannon fire and failing to achieve kills. They reported seeing damage, seeing pieces flying off, watching American fighters trailing smoke or leaking fuel, yet those aircraft kept fighting and eventually escaped. Some pilots theorized that American armor was more extensive than intelligence estimates suggested. Others believed the Americans had developed some new alloy that was particularly resistant to cannon shells. A few reports mentioned that certain areas of the Hellcat's wing seemed especially difficult to damage, describing these sections as reinforced or armored. None of them realized they were describing the Sto-Wing mechanism. The intelligence reports made their way up through Japanese naval command during the summer and fall of 1944. By this point, Japan was losing the air war so comprehensively that tactical analysis seemed almost irrelevant. But some officers still tried to understand what had gone wrong, how the Empire had lost control of the skies so completely in just 2 years. The captured F6F that would arrive at Yokosuka Naval Arsenal in late 1944 would provide some answers. Japanese engineers would examine that aircraft with meticulous care, documenting every aspect of its design. They would measure the armor, they would test the self-sealing fuel tanks, they would examine the engine, the structure, the systems, and they would carefully document the Sto-Wing mechanism, noting its complexity, its weight, and its extraordinary structural strength. The engineering report on the wing fold mechanism would describe it as massively overbuilt for its intended purpose. Japanese engineers, accustomed to designs that minimized weight at every opportunity, found the Sto-Wing almost incomprehensible. Why make the hinge assembly so heavy? Why use such thick structural members? Why create so much redundancy? The report noted that the fold mechanism alone weighed more than the entire wing structure of some Japanese fighters. It seemed wasteful, inefficient. Yet when examined in the context of carrier operations and combat damage resistance, the design made brutal sense. The Hellcat wasn't trying to be light, it was trying to be immortal. One Japanese engineer, in a section of the report that mixed technical analysis with editorial commentary, wrote something that captured the essential difference between American and Japanese design philosophy. He noted that the Sto-Wing mechanism represented approximately 300 pounds of structural weight that contributed nothing to the aircraft's performance. It didn't make the Hellcat faster. It didn't extend range. It didn't improve maneuverability. From a pure performance standpoint, it was dead weight. But that dead weight served two purposes. First, it allowed carriers to store more aircraft, which multiplied American combat power. Second, and this was the engineer's key insight, it created structural redundancy that made the aircraft extraordinarily difficult to destroy. The engineer concluded that Americans were willing to accept weight penalties in exchange for pilot survival and operational flexibility. Japanese designers had made the opposite choice, pursuing performance above all else. The report didn't explicitly state which philosophy was correct, but the implications were clear. The empire was running out of pilots because its fighters didn't bring them home. By late 1944, the tactical situation in the Pacific had become so one-sided that individual aircraft characteristics mattered less than the overwhelming superiority of American industrial production and pilot training. Japan had started the war with perhaps the best-trained naval aviators in the world and some of the most capable fighters. 3 years later, those advantages had evaporated. The elite pilots were dead, the training pipeline had collapsed, and Japanese fighters, even the newer models like the N-1K and the J-2M, were facing not just Hellcats but also the even more formidable F-4U Corsair in increasing numbers. Some battles in late 1944 and 1945 saw Japanese aircraft massacred at ratios exceeding 30-1. These weren't battles, they were execution details. American pilots flying Hellcats during this period describe a strange mix of emotions. There was satisfaction in achieving kills, but also discomfort at how one-sided many engagements had become. Lieutenant Commander David McCampbell, who would become the Navy's top ace with 34 victories all achieved in Hellcats, later described missions where Japanese pilots seemed almost suicidal, pressing attacks against impossible odds with minimal hope of survival. McCampbell once shot down 9 aircraft in a single engagement, a feat that required extraordinary skill and exceptional ammunition management. But it also required Japanese pilots who kept coming straight at him, despite watching their comrades dying all around them. The discipline and courage of those pilots was never in question. But they were flying obsolete aircraft with minimal training against American pilots in Hellcats, who had hundreds of hours of flight time, excellent tactical training, and fighters that could absorb tremendous punishment and keep fighting. The structural resilience of the Hellcat became a defining characteristic that influenced how American pilots approached combat. They knew their aircraft could take hits and survive. This knowledge created a psychological advantage that's difficult to quantify but was nonetheless real. Pilots pressed attacks more aggressively because they trusted their aircraft to bring them home. They accepted combat at less favorable odds because they knew the Hellcat's armor and structure gave them survivability that enemy pilots lacked. They flew into heavy anti-aircraft fire during ground attack missions because they'd seen Hellcats survive damage that would have destroyed other fighters. This aggressive posture accelerated Japanese losses and further tilted an already lopsided exchange ratio. The Sto-Wing mechanism, that seemingly mundane feature designed to save space on carrier decks, had become part of a larger system that made the Hellcat nearly invincible in the hands of well-trained pilots. The mechanism itself never appeared in combat reports. Pilots didn't think about it. They thought about armor, about self-sealing tanks, about engine reliability. But that diagonal fold line, with its massive structural components and redundant load paths, was saving lives in ways nobody had predicted. When cannon shells struck near the wingfold, they hit a section of aircraft that was effectively a fortress. When pilots pushed their damaged Hellcats into high-stress maneuvers to escape pursuing enemies, those wing structures held together because they'd been designed to survive the most violent carrier operations imaginable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The engineering philosophy that produced the Sto-Wing represented something larger than just one mechanism on one aircraft. It represented a fundamental difference in how American and Japanese designers approached the problem of carrier aviation. American designers, led by men like Leroy Grumman, believed that carrier operations were so inherently dangerous that aircraft had to be massively overbuilt to survive routine operations. If you designed an aircraft that could survive thousands of catapult launches and arrested landings, if you built it to handle the worst weather and the most abusive handling, then you accidentally created an aircraft that could also survive combat damage. The extra weight was worth it. The performance penalties were acceptable. Because dead pilots couldn't learn from their mistakes, couldn't pass knowledge to new pilots, couldn't become the aces who would eventually dominate enemy airspace. Japanese designers had started with different assumptions. They assumed skilled pilots could compensate for aircraft limitations. They assumed that dogfighting capability mattered more than survivability. They assumed that a war would be decided in months, not years, so designing aircraft for long-term durability wasn't necessary. All of these assumptions had been reasonable in 1941. By 1944, they'd all been proven catastrophically wrong. The war had stretched into years. Pilot skill couldn't compensate for being outnumbered 10-1 while flying unarmored fighters. And dogfighting capability meant nothing when American pilots refused to dogfight, using speed and altitude to control engagements instead. The Zero had been designed for a war that never happened. The Hellcat had been designed for the war that did happen. The wreckage of Japanese aviation lay scattered across the Pacific by the winter of 1944. Saipan had fallen in July. The Philippines were being retaken. American carriers ranged across the western Pacific with near impunity, striking targets that had been beyond reach just a year earlier. And everywhere they went, Hellcats dominated the skies. The kill ratios continued to climb. By December 1944, the F6F had achieved a combat record unprecedented in naval aviation history. Over 5,000 Japanese aircraft destroyed. 305 American pilots had become aces flying Hellcats. The aircraft accounted for 75% of all U.S. Navy aerial victories in the Pacific War. These weren't just numbers. They represented a systematic destruction of Japanese air power that made the outcome of the war inevitable. But the story of why the Hellcat proved so dominant wasn't just about pilot skill or numerical superiority. It was about an accumulation of design decisions, each seemingly minor, that together created a fighter that was nearly impossible to kill. The Sto-Wing mechanism was one piece of this puzzle. The armor was another. The self-sealing fuel tanks were a third. The robust engine that could run with cylinders shot out was a fourth. The redundant control systems were a fifth. Stack enough redundancy into an aircraft, and you create something that refuses to die even when it should. Japanese pilots discovered this the hard way, mission after mission, as they poured fire into American fighters and watched those fighters simply absorb the damage and keep fighting. Lieutenant Kaneyoshi Muto flew Zeros from Iwo Jima during the winter of 1944 and 1945. He was one of the few Japanese pilots with significant combat experience who survived the war, having accumulated over 400 hours of flight time before the war ended. In post-war interviews, Muto described his experiences fighting Hellcats with a mixture of professional respect and bitter frustration. He recalled one engagement in January 1945, where his shot eye, a 3-aircraft section, intercepted a lone Hellcat that had become separated from its formation. The tactical situation seemed perfect. 3 experienced Japanese pilots against 1 American. They attacked from above, diving with speed advantage, catching the Hellcat pilot apparently unaware. Muto led the attack, opening fire at 300 meters with both cannon and machine guns. He saw his rounds strike the Hellcat's fuselage and left wing. His two wingmen followed immediately, their fire adding to his. The Hellcat took hits across both wings and the fuselage. Pieces flew off. Smoke streamed from somewhere behind the engine. The American pilot rolled inverted and dove, trying to escape. The three Zeros followed, maintaining their speed advantage, firing repeatedly. Muto estimated they collectively fired over 300 rounds of 20mm ammunition and perhaps 1,000 machine gun rounds during the engagement. Many of those rounds hit. Muto could see the damage accumulating on the American fighter, yet the Hellcat kept flying. It didn't catch fire. It didn't break apart. The pilot maintained control despite what should have been catastrophic damage. Finally, after several minutes of pursuit, the Hellcat pilot rolled level at very low altitude and firewalled his throttle. The big Pratt & Whitney engine, despite visible damage, produced full power. The Hellcat began pulling away from the pursuing Zeros, using its superior speed at low altitude to open the distance. Muto and his wingmen chased for several more miles, firing their remaining ammunition, scoring additional hits that accomplished nothing. The Hellcat escaped. Muto returned to Iwo Jima with his wingmen, all three frustrated and confused. They'd done everything correctly. They'd achieved tactical surprise. They'd maintained numerical superiority throughout the engagement. They'd scored dozens of hits on the American fighter, and they'd failed to achieve a kill. Muto's combat report from that day described the Hellcat as extremely durable and noted that conventional tactics may be insufficient against this aircraft type. What Muto didn't know, couldn't know, was exactly where his rounds had struck and what they'd encountered. Some had hit the Hellcat's fuselage, penetrating the aluminum skin but stopping against armor plating or structural members. Some had struck the wings in areas that were lightly built, punching through and causing damage, but not threatening the structural integrity. And some, perhaps a dozen shells during the entire engagement, had struck near or directly on the wing fold mechanism. Those shells had accomplished almost nothing. They'd scarred the surface. They'd dented heavy components. But they hadn't penetrated the structural fortress that existed in that area. The pilot had nursed his damaged Hellcat back to his carrier, landed safely despite hydraulic problems and battle damage across multiple systems, and lived to fly again. The aircraft itself was repaired in less than a week and returned to service. Engagements like this occurred repeatedly during late 1944 and early 1945. Japanese combat reports from this period show a consistent pattern. Pilots reported hitting Hellcats extensively, sometimes expending all their ammunition on a single target, yet failing to achieve kills. The reports use phrases like exceptionally robust, resistant to damage, and structurally reinforced. Some reports specifically mention that certain areas of the Hellcat appeared more resistant than others, noting that hits to the wings near the fuselage seemed to accomplish less than hits to the outer wing panels or tail surfaces. They were describing the Sto-Wing mechanism without knowing it. They were learning through bitter experience that American fighters had structural redundancy in places Japanese designers had never considered necessary. The frustration evident in these combat reports reflected a larger crisis facing Japanese naval aviation. By early 1945, Japan was losing pilots faster than it could train replacements. The training program had collapsed under the weight of fuel shortages, instructor losses, and the simple reality that there wasn't time to properly train new aviators. Pilots were being rushed through abbreviated programs and thrown into combat with minimal preparation. Meanwhile, American pilot training had become systematically excellent. New pilots arrived in the Pacific with over 300 hours of flight time, extensive gunnery training, and tactical instruction that prepared them for the specific challenges of combat against Japanese aircraft. They flew fighters that could survive their inevitable mistakes during early missions. They had experienced squadron mates who could teach them the finer points of combat tactics, and they flew so many missions that survivors accumulated combat experience rapidly. The Hellcat enabled this system. Because it brought pilots home despite battle damage, it allowed them to learn from their errors. A pilot who made a tactical mistake that resulted in taking hits from enemy fire got to make that mistake once, learn from it, and not repeat it. A pilot flying a Zero who made the same mistake often died, taking his potential learning with him. Over time, this difference in survival rates created a vast gulf in average pilot quality. By early 1945, the average American Hellcat pilot had more flight time, more combat experience, and better tactical training than all but a handful of remaining Japanese aviators. The structural resilience that the Sto-Wing mechanism contributed to, that seemed like such a minor factor compared to armor or firepower, was actually part of the foundation that allowed this experience advantage to develop. Engineers at Grumman never understood the full implications of their design decisions. They knew the Hellcat was successful. They knew pilots loved it. They received feedback about its survivability and made minor improvements to later variants. The F6F-5, which entered service in 1944, incorporated various refinements based on combat experience. The engine cowling was redesigned for better cooling, the windscreen was improved, tail surfaces were strengthened, provisions were added for carrying 2,000 pounds of bombs or 6 rockets under the wings, but the basic airframe remained unchanged. The Sto-Wing mechanism continued to use the same heavy structural components, because it worked, because pilots kept coming home. The captured Hellcat that Japanese engineers examined at Yokosuka in late 1944 provided detailed information about American design philosophy, but that information arrived too late to influence Japanese aircraft development. By the time the analysis was complete, Japan's aviation industry was struggling just to maintain production of existing designs. Fuel shortages limited flight testing. Strategic bombing had damaged factories. Critical materials were increasingly unavailable. The engineering report on the Hellcat Sto-Wing mechanism was filed away, read by a few senior officers, and then largely forgotten as more immediate crises demanded attention. In March 1945, the report made a brief reappearance during discussions about new fighter designs that might counter American air superiority. Several engineers suggested that future Japanese fighters should incorporate structural redundancy similar to what the Hellcat demonstrated. But these discussions were academic. Japan lacked the industrial capacity, the materials, and the time to design and produce new fighters. The war would be decided with the aircraft already in service. The final months of the Pacific War saw the Hellcat transition from fleet defense to strike missions. With Japanese air opposition largely eliminated, F6Fs increasingly carried bombs and rockets for ground attack. The same structural strength that made the aircraft resistant to cannon fire also made it excellent for low-altitude strike missions, where anti-aircraft fire was intense. Hellcats flew close air support for the Iwo Jima invasion in February 1945. They struck targets across Okinawa from March through June. They ranged along the Japanese home islands, attacking airfields, shipping, and industrial targets, and they continued to survive damage that would have destroyed lighter aircraft. One F6F returned from a strike mission near Tokyo with 68 holes from anti-aircraft fragments. Another landed on USS Essex with half its left wing shot away, the damage extending into the fold line area. The structural members there had held despite extensive damage around them, allowing the pilot to maintain control and land safely. The crew chiefs and maintenance personnel who kept Hellcats flying developed deep appreciation for Grumman's engineering. They saw the damage their aircraft absorbed and marveled at how the structures held together. They worked on fighters that had taken hits near the wing fold and noticed that damage in that area was often less severe than hits elsewhere. Some maintenance crews started referring to the fold line as the armoured hinge, even though it wasn't actually armoured in any conventional sense. It was just massively overbuilt, and that overbuilding provided protection that armour alone couldn't match. A armour plate stops projectiles by being hard and thick. Structural redundancy stops catastrophic failure by providing multiple load paths, so that damage to one component doesn't cause total collapse. The Sto-Wing mechanism provided the latter, almost by accident. By August 1945, when the war ended, the Hellcat had compiled a combat record that remained unmatched in naval aviation history. 12,275 F6Fs had been produced in just 30 months. They'd flown 66,530 combat sorties and destroyed 5,163 enemy aircraft for the loss of only 270 in air combat. The kill ratio of 19:1 told a story of complete air superiority, but behind that ratio lay countless individual stories of pilots who survived because their aircraft refused to quit. Stories of fighters absorbing damage that should have been fatal. Stories of pilots nursing crippled Hellcats back to their carriers. Stories of maintenance crews patching holes and replacing damaged components, then sending the same aircraft back into combat within days. The Sto-Wing mechanism appears nowhere in the official combat records. No after-action report mentions it specifically. Pilots didn't think about it during combat. They thought about threats, about tactics, about their targets. But that diagonal fold line, with its heavy hinges and redundant structures, was saving lives in every engagement where cannon shells struck near it. And because it was designed to survive thousands of fold cycles under the worst carrier operating conditions, it provided a margin of structural safety that protected pilots even when they didn't know they were being protected. This is how good engineering works in practice. Not through flashy innovations or revolutionary concepts, but through careful attention to reliability, through overbuilding critical components, through creating redundancy that seems wasteful until it saves your life. Japanese engineers who examined the Hellcat understood this intellectually. Their reports describe American engineering philosophy as conservative and prioritizing reliability over performance. But understanding something intellectually and being able to implement it industrially are very different things. Japan in 1944 lacked the industrial capacity to build Hellcat-style fighters, even if designers had wanted to. The empire was resource-constrained, factory capacity limited, and time-desperate. Every fighter had to be as light as possible to maximize performance with limited power engines. Every pound of structural weight seemed like a pound that could have been used for fuel or ammunition or some other combat-relevant purpose. The idea of adding 300 pounds of structure purely for reliability and survivability seemed almost incomprehensible to engineers working under Japan's constraints. Yet that 300 pounds, distributed across the airframe but particularly concentrated in the wing fold mechanism, was part of why the Hellcat dominated the Pacific skies. It was part of why pilots trusted their aircraft. It was part of why survival rates were high enough that pilots could gain experience. It was part of why 305 American aviators became aces flying Hellcats. Not the only reason, not even the primary reason, but part of the complex system of design decisions, industrial capacity, pilot training, tactical doctrine, and strategic advantage that gave the United States complete air superiority by 1945. The Sto-Wing was a piece of this puzzle, a piece that engineers designed to fold wings, a piece that accidentally provided structural protection, a piece that contributed to one of the most lopsided victory ratios in aviation history. The Battle of the Philippine Sea, where this story began, became the archetype for what American naval aviation could achieve with the right aircraft. Nearly 500 Hellcats had participated in that single day's combat, creating a defensive barrier that Japanese attackers couldn't penetrate. The ratio of losses, approximately 15 Japanese aircraft destroyed for every American loss, demonstrated what happened when well-trained pilots flew durable, well-designed fighters against less experienced opponents in fragile, obsolescent aircraft. The battle marked the effective end of Japanese carrier aviation as a meaningful force. The carriers themselves survived, but the aircraft and the trained pilots to fly them were gone. The few surviving aviators returned to their units traumatized and demoralized, telling stories of American fighters that wouldn't die, that absorbed hits and kept fighting, that seemed nearly invincible. Those stories were accurate, not because Hellcats were perfect. They weren't. The F4U Corsair was faster. The P-51 Mustang had longer range. The F8F Bearcat which entered service too late to see combat, was more maneuverable, but the Hellcat was good enough in all categories while being exceptional in durability and ease of operation. It was the right aircraft at the right time, designed for the specific challenges of carrier-based combat in the Pacific. And one of its key features, the Sto-Wing mechanism that seemed so mundane, contributed to its success in ways that nobody had predicted or intended. Sometimes engineering breakthroughs come from revolutionary innovations. Sometimes they come from careful attention to details and overbuilding critical components. The Sto-Wing was the latter. A simple mechanism made extraordinarily robust, contributing to an aircraft that refused to quit. The legacy of the Hellcat and its Sto-Wing mechanism extends beyond World War II. Modern carrier aircraft still use folding wings for the same reason Grumman developed them. Carrier deck space is precious. The Super Hornet, the Navy's current frontline fighter, folds its wings using a mechanism descended conceptually from the Sto-Wing. The design has evolved, becoming lighter and more efficient, but the fundamental principle remains: a skewed axis fold that reduces space while maintaining structural integrity. Engineers still overbuild these mechanisms because carrier operations remain violent and demanding. And though modern materials and design tools have reduced the weight penalty, folding wing mechanisms on carrier aircraft are still among the strongest structural and components in the entire airframe. Pilots don't think about this. They think about missions, about threats, about returning home safely, but when battle damage strikes near a wing fold and the structure holds together, when systems survive that should have failed, when an aircraft makes it back to the carrier despite damage that looks catastrophic, that's engineering doing its job. That's redundancy saving lives. That's the legacy of engineers like Leroy Grumman, who understood that sometimes the best way to save weight is to add it in the right places, to build structures strong enough that they never become the weak point, to create margins of safety that seem excessive until they're needed. The F6F Hellcat was retired from frontline Navy service shortly after World War II ended. The F8F Bearcat, which had been designed as its replacement, served briefly before jets took over carrier decks. But the lessons learned from the Hellcat's success influenced American naval aircraft design for generations. Pilot survivability became a primary design consideration. Structural redundancy became standard practice. The ability to absorb battle damage and return home became a requirement in specification documents. These weren't abstract concepts. They were lessons written in the survival rates of Hellcat pilots during the Pacific War. Lessons that said durability matters more than elegance, that bringing pilots home matters more than pure performance, that sometimes the best fighter is the one that refuses to quit. Today, only a handful of airworthy Hellcats remain, carefully maintained by museums and collectors. When they appear at air shows, elderly veterans sometimes attend. Men now in their late 90s or older who flew these aircraft 80 years ago. They stand beside the broad-winged fighters, running their hands over aluminum skin, remembering missions and friends and the aircraft that brought them home. Sometimes, very rarely, former Japanese pilots attend the same events. Old men who once tried to shoot down these American fighters, now united with their former enemies in the universal bond of military service and old age. The conversations between them are remarkable. The Americans thank the Japanese for their courage. The Japanese thank the Americans for treating prisoners with dignity. And both groups acknowledge the aircraft that stands between them, the flying fortress that proved tough enough to absorb everything the Japanese could throw at it and still brought its pilots home. The fighter with the distinctive diagonal fold line across its wings, that fold line that nobody thought about during combat, but that saved countless lives through structural redundancy nobody knew existed. The Sto-Wing mechanism that Leroy Grumman invented using paper clips and an eraser, that became one of the most successful engineering features in aviation history, without anyone quite realizing it. The simple diagonal hinge that made the Hellcat nearly indestructible in ways its designers never intended. That's the story. Not of a revolutionary breakthrough or a dramatic innovation, but of careful engineering, attention to reliability, and the accumulated effects of dozens of design decisions that together created a fighter that changed the Pacific War. Japanese pilots never expected that a mechanism designed to save space on carrier decks would make F6Fs survive 20mm cannon hits. They couldn't have expected it. Nobody at Grumman expected it either, but that's what happened. The Sto-Wing, with its heavy hinges and massive structural components, became part of the reason why the Hellcat was so difficult to destroy. Not armor, not some revolutionary material, just solid engineering, redundant structure, and the willingness to accept weight penalties in exchange for reliability. In the brutal mathematics of aerial combat, that exchange proved to be the difference between winning and losing, between pilots who survived to become aces and pilots who died on their first mission, between an aircraft that dominated the Pacific skies and one that became just another footnote in aviation history. The Hellcat wasn't the fastest fighter, it wasn't the most maneuverable, it wasn't the most advanced, but it was the toughest. And in 1944 and 1945, in the skies over the Pacific, toughness was the quality that mattered most. The Japanese admitted as much, even as it cost them the war. Their combat reports, their engineering analyses, their pilot accounts all described the same phenomenon. American fighters that wouldn't die, that absorbed hits and kept fighting. That brought their pilots home mission after mission. The Hellcat created that reputation. And the Sto-Wing mechanism, that humble folding mechanism designed with paper clips and an eraser, was part of the reason why. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.